Today's problem is shortest path using at most one curved edge. Given an undirected connected graph with v vertices numbered from 0 to v minus 1 and e double edges, oh I see, represented as a 2D array edges. Each double edge is represented by a tuple x, y, w1, w2. Indicates there are two edges between vertices x and y, a straight edge with weight w1, a curved edge with weight w2. You are given two vertices, a and b, and you have to go from a to b through a series of edges such that in the entire path you use at most one curved edge. Your task is to find the shortest path from a to b satisfying the above condition. If no such path exists, satisfying this restriction, return -1. Guarantee the shortest path will fit into a 32-bit integer. Okay. Well, let's see. So here's an example. We want to go from 1 to 3. 1 to 3. 1 to 3 directly is not that great. 6, 5. 5 is the best we can do there. If we take the straight edges from 1 to 3, through 0 we have 1, and 3 that is 4, but we are allowed to use one curved edge, so we could go 1 and then 1 and get an output of 2. Okay, what about this one? This one's a little bit too simple. We'll just use one curved edge for 1 constraints. Number of vertices between 1 and 10 to the 6th, 1 million. Number of edges between 0 and 1,000,000. A and B, the start and end vertices will be between 0 and v minus 1 inclusive. Let's see, edges I0, I1. Oh, okay, those are the vertices. So, okay, say the vertices will be in a valid range, and the edges, the edge weights will be between 0 and 10 to the 4th, 10,000. Expected complexities, v plus e times log v, auxiliary space v plus e. Okay, graph shortest path. All right, we're going to do something a little bit different here. So we have graph, we have shortest path. Let me check something here. The complexities here. V plus e log e, v plus e log e, v plus e. Okay, so v plus e log v. This is log e. All right. Graph shortest path. There's the best algorithm for single source shortest path is Dijkstra, provided we don't have negative edges, which we don't. Dijkstra can't handle negative edges. Okay, what we're going to do is, this is very similar to something like this. What was this one? Number of ways to arrive at destination. Okay, we were able to use Dijkstra for this with a small modification, the small modification being that when Dijkstra finds a shortest path, if it finds another path with the same, another path of the same distance, it just ignores it. It says, well, we've already got it, okay? So we just modified that to say, okay, if we find another path of the same distance, we're going to keep track of it. So that will give us the number of ways to arrive at the destination. This one that we're working on might be a little bit more complex. Might be a little bit more complex modification, but I'm going to take this and I'm going to use this as a starting point. Now you don't have the luxury of doing this with at an interview, but I think it might be good to see how the basic structure of this algorithm stays the same and we can modify it to we can modify it to be used in different coding challenges. All right, so let's put this whole thing in here. All right, so we start out with an edge-weighted graph. We have to put the we got to put the edges in. Yeah, let me go here. Can we see all of this? Not quite. Let me scoot it over a little bit. All right. So we have an edge-weighted graph. We have edges. Now the edges are a little bit different here. In this one, we just had node, node, weight. Now in this one, we have 2 nodes and 2 weights. So we need to change the add edge method. So let's say for each edge, let's add an edge, but let's do it by, passing in the array, the 4-element array, and modifying add edge to process it. So down here in the graph, add edge. All right, so in this case, edge is not an edge object. Edge is an integer array. Let me see what we have to do with edge here, because we're going to have to change edge as well. All right, so for this one, I'm going to simplify this a little bit and just say we have a variable called, and this is going to go, these will go in the adjacency list. We have a variable called 2. That will be the index or the vertex that this edge goes to. All right, now we need 2 weights here. We have a straight weight, and we have a curved weight. Okay, that's it. All right, so then we'll say this 2 equals 2. This straight weight equals straight weight, and this curved weight equals curved weight. And again, to kind of simplify this, I am going to, because we don't have to, we don't need to order the edges like this. The edges are not what's going in the priority queue this time. All right, so there's our edge for this problem. It has a destination node and 2 weights, and so we can put that into adjacency lists. All right, so add edge would then work like this. We'll create an edge with new edge E at 0. That's the first vertex, and then E2 and E3. Those are the 2 weights, and we're going to need another one of these. Now this we don't need, but we're going to need another one of these to handle both edges. Okay, so this one is going to, well, we'll have one that goes from the first vertex to the second vertex, but it's undirected, so really we need to put it in there twice. So we also have an edge going from the second vertex back to the first index, first vertex. The weights remain the same. And then for the first one, we need, let's see, adjacency list, get, all right, so this has E at 0 in the adjacency list. So we're going to put it in the E at 1 adjacency list and add the edge, right? This one is going to go from 0 to 1 and add the edge. Okay, and then we don't need these. Good. Returning the adjacency list is the same. I think everything else about the edge-weighted graph is the same. All right, let's go back up to the top. So we have the graph. We've added the edges to the graph. What we need here, distance. We need a 2-dimensional distance array. We need one index for the straight weight distance, and we need one for the curved weight distance. Any weight that includes a curved distance. So let's say int dist2 equals new int v2. So for each vertex, we are going to have 2 distances. The array's fill is not going to work that way, and ways is actually a holdover from the previous one, so we don't need that either. We do need integer max value. I'll put it right there for now, and we'll just say for int I equals 0, I is less than v, I plus plus. What is going to be in there? Dist2 I at 0 equals max value and I at 1. That'll be the curved weight. That is also initialized to max value. All right, so dist2, and what are the inputs here? So A is our source vertex. We are finding a path from A to B using at most one curved edge. So dist2, the starting vertex is this. And again, ways is a holdover that we don't need anymore. The distance from the starting node to itself is 0. Whether or not we have a, well, it doesn't matter. It's for, straight length, curved length. But the initial distance is 0. Priority queue. Pair. What we were using for the priority queue was a pair. Where is the pair down here? Just of node and what we were calling time or distance. So for each, let's see. Yeah, so for each pair, node and distance, we would add nodes to the shortest path in increasing order of distance. So shortest distance first, which is the way that Dijkstra works. In this case, we are not going to be able to use pair because we have 2 distances. So we're going to have to change this up a little bit. I mean, it's still a helper class, but it's not really the same thing. Let's just call it state. Okay, so we have a node we have a distance, but we also have to know at any time whether or not we have used a curved edge. Okay, so that is our state. What node are we looking at? What is the distance to that node? And curved edges used. Maybe that could be Boolean, but we could just say 0 or 1. So this node is node. This distance is distance, and this curved edges used is curved edges used. All right, so now we have the state. We are going to, in the priority queue, keep state objects. Comparing int. We were calling it time before, but in this case, we're actually calling it distance. But same thing. The priority queue keeps the nodes in order of increasing distance. All right. So to get things started here, we start with the only node that we really know anything about, which is the node at the node at, we don't want to start at 0. We want to start at A. That's the starting node. Starting node is A. The distance from A to A is 0, and the number of curved edges used is 0. All right? So, iterating through the priority queue, state, and then we have int u equals current node, int d equals current distance, int, let's call it k equals current curved edges used. This is okay, but we need the other index. If the distance is, if d is greater than the distance that's already in the distance matrix, that means we've already processed it. We've already found a shorter path. So we're just going to continue. And we're going to look at the nodes that are adjacent to this node. Initially, we're just at the start node. We'll look at the nodes that are adjacent to the start node. What is that, by the way? This one we start at 1, so we would look at adjacent nodes for 0 and 3. But okay, so for neighbor, the neighbor is actually the neighbor. What is in the adjacency? What is in the adjacency I'm sorry, what is in the priority queue? It's state. Okay, so what we want is, okay, hang on a second, I gotta think about this. Okay, so let's do it here. These are edges. Right here. So this vertex is going to be 2. So edge has 3 properties: 2, distance, and wait. 2. I'm sorry. What do the edges have now? Edges have 2. Oh yeah, 2 straight weight and curved weight. Okay, 2 straight weight and curved weight. All right, W equals neighbor 2. Now we've got to account for, we have to account for straight weight and curved weight. So first let's try a straight weight. So we have this D, that is our current distance to this node. All right, if D plus neighbor dot straight weight is less than the distance to, we need the index here, then dist to W K will be, well, it'll be this, right? If D, current distance plus the straight weight to the neighbor is less than the distance that we already have to node W, then the distance to node W is going to be D plus neighbor straight weight. And ways is gone. And we are going to offer a new state, which is going to contain the state is going to contain node distance and curved edges used, which has not changed. Okay, now this else if equal was a holdover from the previous solution. Now, what we need is we got to handle the curved weights. Okay? Curved weights. If K equals 0, why is that? Because K is the number of curved weights. And if K is not 0, then we can't use a curved weight. So first we check and see, is K equal to 0? Right? If it is, and the neighbor curved weight is less than, and now we're not using K, we've got to use the curved weight path, right? If D plus the curved weight path is less than W, distance to W using a curved weight path, then we're going to update the distance to W using a curved length path. And that is going to be D plus neighbor curved weight. P, Q, offer, new, state. Okay. Again, there's no option here. We're dealing with curved weight, so this has got to be curved weight 1 and 1. All right. Return ways. We're not going to return ways. Again, that's a thing of the past. What we're going to return is math min of dist to B, which is our destination node, with the straight weights, or distance to B with curved weights. And I think that's all the updates that we need to make here. How is this different from Dijkstra? Well, we're really maintaining two distance how should I say this? We're really maintaining two distance arrays. One is straight edges only. One is including a curved edge. Okay? We have to be careful with the way that we handle curved edges here. So when we come through here, it's not as simple as it ordinarily would be, where we just check the distance. We have to check the distance with the straight weight and the distance with the curved weight. We have to check and see that we haven't already used a curved weight. I think I'm over talking this at this point. Let's and actually, let me look at one more thing here, because when I put the edge in, wow. Okay, so I'm surprised that actually compiled. Okay, so this is not right. The inputs here should be 2. There should be straight weight, and they should be curved weight. All right. Yeah, let me do one more compile on that. All right, so that comes back and it's okay. All right, well, in that case, let's run it. Okay, so that's it. It's another Dijkstra algorithm, yeah, again, if you have single source, shortest path, graph problems, you don't have negative weights, then Dijkstra is likely to be your best choice. So, you know, get comfortable with it. Get comfortable with some of the, you know, variations that we've done with it. Which, yeah, and that's it. So you can like the video, you can subscribe to the channel, subscribe to notifications, and we'll see you next time.